More than 70% of the Earth is covered by water. And in the oceans and rivers of our planet, nearly half of all its animal species live out the remarkable cycles of their existence. For each of these creatures, survival and reproduction hinge upon an elegant dance, where movements are precisely choreographed and performers superbly equipped to face daunting challenges. This is a realm where biological wonders reflect the highest levels of purpose and design, and extraordinary clues to the mystery of life shine like stars throughout a liquid universe. Albert Einstein once said that the most beautiful thing we can experience is the mysterious, because mystery is the source of all true science. Today, after centuries of research and debate, science continues its quest to explain what is perhaps the greatest mystery in the universe. How do we account for the origin, diversity, and complexity of life on Earth?
You know, that's always been the big question, and I think there are two primary explanations. Two competing worldviews that have attracted the most attention and, frankly, generated the most controversy. The first we can call scientific materialism. This is the view that life is the result of physical interactions between matter, energy, and blind, undirected processes like natural selection. It's actually the foundation of Darwinian evolution. The second explanation is based on the view that every living organism is the product of purpose, plan, and a creative intelligence that exists outside the natural world. So science faces the challenge of trying to determine which one of these conflicting ideas is true. Now today I'd say that most biologists favor the view that all life originated in the ocean and then gradually evolved from simple to complex into corals and jellyfish and sharks and eventually human beings. But if you really study the animal kingdom and all of the incredible behaviors and biological engineering, I think there's a significant body of evidence that challenges the materialistic position. Evidence that points to realities like purpose, design, and imagination. And it isn't that hard to find. In fact, it's everywhere, just waiting to be discovered. So get in a boat, go to the beach, go out on the water, go beneath the water, you're going to see design.
Off Southern California, we have the greatest density of dolphins per square mile of anywhere on the planet. We have huge herds out here, up to 10,000 dolphins. It's like being in a herd of stampeding horses, and you're like right in the middle of it, and they're just... It's just beautiful, breathtaking, and when you see it, you never forget it.
Since 1994, Captain Dave Anderson has owned and operated one of the most successful dolphin and whale watching companies in the world. He has devoted thousands of hours to the study of dolphins off the coast of Dana Point in Southern California.
They will come right over to our boat to ride the pressure wave that's created by the boat moving through the water. We call it bow riding or boat surfing. And when they show up, it's like, hey, my friends are here, you know? And it's just a wonderful feeling. They are very efficient swimmers, and they can get up to speeds of close to 30 miles an hour. And they're such masters of their environment, perfectly suited for being in the ocean. I love to be able to share these animals with other people and see their reaction. I have seen grown men who have cried when they have seen the beauty of a dolphin swimming on the front of a boat. Everything is so choreographed and perfect, this synergy that goes on between the animal and the people.
A dolphin's grace and efficiency are the products of several factors, including a powerful tail that generates 5 times more forward thrust than an Olympic swimmer, a streamlined body ideal for cutting swiftly through the water, and glassy smooth skin that is shed and regenerated completely several times a day to remove barnacles and other organisms that could cause resistance at high speeds.
Dolphins live in pods, herds, or schools, and they have an amazing social network that allows them to really work together as a team. They live in these big pods partly for safety. Obviously, their safety in numbers, they can keep an eye on each other that way. And also, it helps when they're feeding to have several animals so they can spread out when they're looking for the fish.
When a hydrophone cable is towed through the ocean, the dynamics of the pod are even more apparent.
I mean, we can hear that pod from miles away. And as the dolphins approach the hydrophone, the sounds get unbelievably loud. The clicks all sound like a Geiger counter. And then you'll hear, it almost sounds like a radio trying to tune in with all the whistles and the clicks going on. The whistles are how the animals talk to one another, and so these dolphins are communicating to one another through their whistles, and then they've got the clicks, and the clicks are how they're finding their prey.
The animal's distinctive clicks are critical to its survival. For a dolphin's world is often one of limited visibility, and immediate recognition of food, allies, or enemies hinges upon sensory mechanisms other than vision.
You can't see very far underwater, but sound travels 4 times faster underwater than it does on land. So they're able to use sound to see.
Echolocation, or biosonar, is a complex biological system. Dolphins use it much like a submarine relies on sonar technology to navigate through environments where visibility is marginal or non-existent. In basic terms, a dolphin's echolocation works like this. The animal produces a series of low and high frequency sounds that are transmitted through its forehead. After these sonic waves hit an object, echoes bounce back. The greater the distance, the longer the delay in their return. When the dolphin receives the reflected signals, it forms a mental image of the target's location, size, and speed.
When they're chasing a fish, they'll go into a huge school of fish and they'll zero in on one fish. and they'll follow that single fish until they catch it. And if that fish jumps out of the water, they're right there jumping out of the water with it.
Echolocation requires several component parts, each designed for a specific function. When integrated, they form the most efficient sonar system on Earth, natural or man-made. Dolphins have no vocal cords, yet they produce a wide range of sounds. The process is pneumatically driven, controlled by the flow of air. Rising to the surface of the ocean, the dolphin exhales, then takes a quick breath. The instant the animal submerges, the blowhole shuts tightly as inhaled air rushes through the nasal passages on its way to the lungs. The engine that drives sound production is the larynx, a piston-like organ covered by muscles. It controls the flow of air through twin passages in the skull, each sealed by a retractable plug. When the larynx is pushed upward, the nasal plugs automatically open and air moves freely toward two sets of flaps called the phonic lips.
The phonic lips are the main sound generators, and they're designed to work individually or in unison. When the pressurized air hits the lips from below, they vibrate rapidly and produce bursts of the high and low frequency clicks at rates up to 2,000 clicks per second. It's an action that's been compared to the vibrating lips of a trumpet player blowing through the mouthpiece of his instrument.
Once air passes through the phonic lips, it is stored in pairs of inflatable sacs. When these sacs are full, they quickly deflate as muscles squeeze the air back down the system, past the open nasal plugs, and back into the lower cavities of the skull. Responding to the change in pressure, the larynx retracts, creating space for the recycled air. When the skull cavity refills, the larynx elevates to increase the air pressure. This triggers the nasal plugs to open, and a new cycle of clicks begins.
By recycling the inhaled air, the dolphin can delay having to surface for another breath. That way, it can continue to echolocate for more than 10 minutes. This entire system operates with critical balances and regulation. Every component has to work perfectly within fractions of a second.
The efficiency of sound production is also evident in the transmission of clicks toward potential targets. The vibrations of the phonic lips are reflected off the air sacs and bones in the skull, then pass through the melon, an organ that fills most of the dolphin's forehead. The melon is highly flexible, and its shape is adjusted to fine-tune the transmission of sound through salt water. It is an acoustical lens, focusing sound waves into cone-shaped beams.
If something is far away, they focus their sound and make it more of a low-frequency sound because low-frequency sounds travel further. And when something is nearby, they use a higher frequency sound, and that gives them more detail.
The melon can concentrate acoustic energy by a factor of 4. When the beam hits a fish, it reflects, and the third phase of echolocation begins. The returning echoes are detected and channeled through the dolphin's teeth and lower jaw that function as antennae. This energy is amplified as it travels through large masses of tissue on the jawbone and onto mechanisms in the middle and inner ears. From the inner ear, signals are then transmitted through the auditory nerves to the brain, where they are analyzed in milliseconds. The dolphin interprets this data to produce a three-dimensional image of its target, complete with detailed information about its speed, texture, and shape. How well does echolocation work? In control tests, a dolphin can determine the difference between a golf ball and a ping pong ball based solely on the density of each object. And on the seafloor, it can find small fish buried 3 to 6 inches below the sand.
A dolphin can find a BB at the bottom of a swimming pool, blindfolded. It can see inside of things. It's an amazing device, and if somebody had invented this and had it working as well as the dolphins, they'd make billions of dollars.
Think about echolocation from a problem-solving standpoint. What do you need? I've got to make the sound, number one. Number two, I've got to transmit it. I've got to get it out into the environment. All right, now I've got echoes coming back. Those have to be received, but that's not enough. I've got to process them. I've got to take that incoming information and turn it into something that I can actually use and understand. Making the sound, transmitting it, receiving it, and processing it are necessary elements of echolocation. And if you take away any one of them, let's say we take away transmission, it doesn't matter if you have the other three, you lose the system as a whole.
The challenge of building a complete system grows when the 4 phases of echolocation are broken down into their specific components. For to create the entire mechanism, each of the hundreds of individual parts required must be integrated and fully functional simultaneously.
So you've got all these different components for the sonar, and how does the dolphin know how to use this equipment? That's where instinct comes in. They not only got the hardware, but they got the owner's manual along with it. Instinct is a set of instructions on how to use the equipment, and it has to know that from the second it's born. All of this stuff happens automatically, and it's perfectly set up. It's like you look at it and you say, of course, that's the way it's supposed to work. So it's pretty hard to believe that this all happened by chance and natural selection, especially when each individual part is meaningless without the whole.
As a creative agent, natural selection is severely limited. By definition, the process uses random genetic mutations to slowly build or modify organisms through trial and error and small, gradual steps. Each incremental change is made blindly, without any sense of an ultimate purpose or objective.
What it cannot do is visualize a distant functional endpoint and say, well, I'll need this part, and I'll need this part, and I'll need this part. Any evolutionary process you consider, any materialistic process you can consider, has no foresight. It can't see 5 years, 5 seconds, 5 milliseconds into the future. For that, you need a mind. Only minds, only intellect, only a conscious, purposeful intelligence has the ability to say, that's my target, how can I hit it, what would I need to bring together to do that? That's what we do, that's what designers do, that's what minds and intellects do. Undirected physical processes can't do that. This is rational, it's reasonable. It's taking the evidence and saying, what's the best explanation for what I see?
Each of these hatchling sea turtles is smaller than the hand of a child. Yet they are about to embark on a migration that will span decades and thousands of miles. It is a journey rich in evidence of purpose and design. After instinctively racing across the beach, the turtles will swim almost non-stop for the next 48 hours in an attempt to escape predatory birds, crabs, and fish that line the shore. But immediate survival is not their only objective. During these first 2 days, they will make critical preparations to spend the rest of their lives in the open sea.
Navigating in the open ocean is not easy at all. So from the moment a turtle hatches, there are elements imprinted in that turtle's head that tell it not only about things that it needs to learn, but places that it needs to go automatically. It's there. It's in the system.
Sea turtles migrate through the Atlantic, Pacific, and Indian Oceans, usually alone and without the benefit of significant visual landmarks. To navigate, they rely on a biological system calibrated to work in concert with an invisible shield that surrounds the Earth. Our planet is constantly bombarded by high-energy particles emitted from the sun. We are protected from this deadly barrage by a magnetic field that extends more than 40,000 miles into space. This phenomenon has been compared to an enormous bar magnet, with field lines that flow upward from the southern hemisphere and then wrap around the Earth. Each line intersects a different point on the Earth's surface at a specific angle and intensity. They are strongest at the poles and weakest at the equator. Together, they create a distinct pattern that can be charted as coordinates for the latitude and longitude of any location on the planet.
From the moment they hatch, we think that they may be imprinting on magnetic fields. They're able to detect both intensity as well as the angle of inclination for the potential to imprint on that particular nesting beach and a very specific latitude and longitude.
Once a turtle imprints the geomagnetic coordinates of its birthplace, it begins a journey that will lead to a feeding ground it will use throughout the rest of its life. For a turtle born in Costa Rica, for example, this home range could be a coral reef in the Dominican Republic more than 1,000 miles away. As a hatchling swims and drifts through the Caribbean, it continues to imprint a series of coordinates on a magnetic map inherited at birth and stored within its brain.
Once the turtles enter the water, they are detecting magnetic fields as they're drifting. So they're obviously picking up waypoints along their drifting existence over those first 2 years or so. And it's those waypoints that essentially they're going to use in a reverse manner when they leave the foraging grounds 15, 18, 25 years later to then make their way back essentially to the nesting beach.
The young turtle's development from hatchling into juvenile includes an increasing reliance on an array of internal compasses embedded in its head. Microscopic cells enriched with crystals of magnetite react to the Earth's magnetic field by aligning north.
It's a little tiny magnet. And typically what magnetite will do is it will align like the needle of a compass. It tells them what their heading is, and it tells them something about where they are at that moment.
So they need to be able to know what direction they're moving, but they also need to be able to know where they are at any point in that journey.
After a turtle reaches the feeding grounds, it will often stay for a decade or more while growing to maturity. Depending upon its species, an adult can weigh from 80 pounds to nearly a ton. And when it is ready to reproduce, the turtle sets its course for the beach where it was born. Throughout this return trip, it will again rely upon its internal compass and map. To find its way home, the turtle follows the coordinates it originally imprinted years earlier, but this time in reverse order. Then, when it nears land, it identifies the specific location of its natal beach with another navigational aid, its sense of smell.
Turtles may actually be detecting certain cues, that is chemicals in the water that may have come from the nesting beach, molecules of mud or sediments. They've had to lock that information up somewhere, but then when they turn around after 25 years to come back to the nesting beach, that's the point at which that information has to come back to the brain and say, okay, remember those scents, remember those molecules from 25 or 30 years ago, and now is the time to start thinking about and looking for those cues. And that may be another way for turtles as they get closer and closer to the nesting beach to recognize that they're in the right spot.
Every year, this scene plays out on tropical beaches throughout the world. One by one, adult females crawl out of the ocean to the shore where they emerged as hatchlings. They will dig nests and each lay hundreds of eggs, then re-enter the sea to follow an imprinted map back to their feeding grounds on a migration cycle they will repeat dozens of times during the next half-century.
As a scientist, I love being able to ask questions about intricately designed systems and pursue those answers until we get to some kind of conclusion. This whole idea of migrating thousands of kilometers across open oceans. It's very difficult to imagine, but turtles are still nevertheless able to find their way back to sometimes within meters of where the nesting beach may have been.
Salmon certainly are an icon for the Pacific Northwest. When you look at what a salmon does, the incredible journey it takes, starting in a stream, going out into the ocean for 1,000 miles or more, all of the possibilities of it not returning, and then finding its way to the river mouth, traveling, in some cases, hundreds of miles up a river system, getting beaten up and bruised. Just keep pushing on, enduring to find that one tributary where it's going to lay its eggs. It's truly incredible.
Fishery biologist Glenn Gately has devoted much of his career to the conservation of the Pacific salmon and the study of its life cycle. There are 5 different species of the fish, and for each, a new generation begins in the gravel beds of rivers and streams throughout the northwestern United States and Canada.
First of all, the female will dig a red, which is a depression in the gravel, deposit its eggs, fertilized by the male at the same time, and then the female moves upstream a little bit and digs another one, and the gravel from that covers the one downstream, and the female may do that 3 or 4 times. So the red is actually contains several pockets of eggs.
After hatching, the young salmon stay near their nests, but their native streams lack sufficient nutrients to sustain their development through adulthood.
For salmon to grow into the rather large fish that they end up being, they need more resources that are available in those little streams. So they migrate out into the oceans. They start exploiting all of the food resources that are available there to grow and develop so that they can come back and reproduce again in the freshwater rivers.
In preparation for their time at sea, these small freshwater fish must adapt their biology to survive in saltwater. Then enter an ocean they've never seen, travel thousands of miles, and find their way back to the location where they know they can spawn successfully, the gravel beds where they were born. 2 sophisticated navigational systems are required for this migration. The first is based on the salmon's acute sense of smell and its ability to collect information about its environment as it heads downstream to the Pacific Ocean.
The fish, when it's a juvenile, is imprinting, first of all, on where it's rearing. And then, as it heads down the river toward the ocean, it's picking up cues in these different tributaries along the way. They're imprinting on the odors, the smells in the water, coming from the soil, the water percolating through the soil into the stream, the plants that are in the creek, all have distinct odors. And the odors are very specific. And all of this is being recorded in its memory bank. And as the fish move down the river with these constant signals going in and being processed and going all the way to the brain, a map is being formed.
As the salmon enter the Pacific, this chemical map is preserved and stored. Years later, it will be activated to ensure the survival of their species. During their time at sea, the fish form schools and grow rapidly as they feed on a bounty of marine life. Throughout this stage of their migration, they travel in huge counterclockwise arcs that can extend west, halfway to Japan. Then, when their reproductive systems are fully developed, they instinctively head back to the coast. This return to the exact location of their birth begins with a vital choice. After years in the ocean, each salmon must first identify the mouth of the correct river system that will eventually lead it home.
There's a lot of rivers that empty in along the Washington coast and the British Columbia coast, Oregon coast. Altogether, there must be hundreds of different river systems that it has to choose from.
It's absolutely essential for these salmon to find the right river, the river that they came out of when they were juveniles. Now, like turtles, they use magnetic navigation to get themselves back to the right spot. They have memorized what the magnetic coordinates are at the mouth of the stream that they came out of. And when it comes time to reproduce, they head back towards those magnetic coordinates.
Every September, millions of sockeye salmon congregate here, at the mouth of the Fraser River in Vancouver, British Columbia. 3 years earlier, they swam through these waters before entering the Pacific Ocean. Now they have returned to begin the final leg of their migration. A journey that will end with the new generation.
As the salmon approach the magnetic coordinates that tell them approximately where the river was that they came out of as juveniles, once they've gotten to that spot, they can start smelling the natal river, the river that they came from, and they start heading up that river based on chemical cues that they're picking up by smelling the water.
This chemical map will lead many of the sockeye more than 300 miles inland to the Adams River, a tributary of the Fraser and the place where they were born. Averaging almost 18 miles a day, they relentlessly move upstream. To reach the Adams, they will expend every reserve of strength, battling their way over rapids and rocks in the shallow stream beds. The sockeye are so focused on their objective that after leaving the ocean, they do not eat again. Driven by the instinct to spawn, they follow the trail of odor molecules that grows progressively stronger as they get closer to home.
Then it starts moving up the river, and it's like playing back what it had imprinted going down. It's pulling on that map, and then as it travels up the river, it's remembering, going by this tributary and that tributary, and it has to, no doubt, pass through other tributaries that just don't have the exact smell that it's looking for. But it's zeroing in, eventually, on that exact tributary where it was hatched out of the gravel, where it started its life.
The biological engineering required to interpret these chemical signals is stunning. The salmon constantly analyzes its route by testing the molecular composition of the water that enters its nostrils. In nasal cavities on both sides of the fish's head, flanges of tissue form olfactory organs. Each flange contains 500,000 tightly packed cells. Many of them support cilia that reach out into the water like antennae. And the cilia are embedded with odorant receptors, molecular machines that help identify specific chemicals in liquid.
The water contains odorant molecules, and what's going on is different streams are putting down different combinations of odorants. There's a lock and key kind of relationship between one kind of odorant and one kind of receptor.
Each type of odorant has a distinctive shape and composition. As they flow through the nasal cavity, they make contact with the cilia. If an odorant fails to match a receptor's precise criteria, it deflects. But if its structure is correct, the molecule fastens tightly into the binding site.
The shape has to be exactly right, and the charge distribution has to be exactly right. And then it fits in there like a glove. And that's when the signaling cascade begins.
These connections trigger electrical impulses that instantly flow down the nerve cells and out of the cavity. The signals are relayed through a maze of wires attached to the olfactory bulb, a biological switchboard that processes a torrent of information about the salmon's environment. Inside the bulb, hundreds of receivers interpret and organize this data, then send it on to other areas in the brain that will compare it to the chemical map compiled years earlier, when the juvenile sockeye first swam to the sea.
They can probably detect one odorant molecule on the order of parts per billion, maybe parts per trillion. Who really knows? What we do know is what they're looking at is the overall signal. And if the signal fits with the memory perfectly, then the fish knows this is the river, that's the one I'm going to swim up.
17 days after leaving the Pacific Ocean, the sockeyes reach Shuswap Lake and the confluence of the Adams River. Here they rest before making their final push to the gravel beds where they hatched 4 years earlier. From the air, an oscillating wall of salmon is visible along the shore. Thousands of fish have followed the same chemical trail to reach the inlets of this delta. Their odyssey is now hours from completion. In the amber glow of a Canadian autumn, the sockeyes disperse over 8 miles of shallow flowing water. It is an ideal place to build their nests, lay and fertilize their eggs, and ensure a new generation.
The system that salmon use as they head upstream seems almost impossibly accurate. Literally millions of them successfully make these journeys and successfully reproduce so that we see the whole cycle repeated over again. I'm awestruck by it.
Biologists have long marveled at the mysteries of animal migration. And in the process, they have discovered that navigational systems based on an acute sense of smell or the Earth's magnetic field are not limited to salmon and sea turtles. Comparable systems also appear in a variety of diverse organisms, including mammals, insects, and birds. Is it possible that natural selection can explain the origin of such elaborate biological mechanisms? Not once, but multiple times throughout the animal kingdom.
All of these different organisms have one kind of problem that they have to solve. They have to be able to navigate. And as long as you're constrained by that Darwinian view of reality, you have to explain it via that mutation selection kind of model. But how many times can we realistically expect random changes at the genetic level, coupled with unguided natural selection, to come up with the same solution? Darwinian natural selection is blind. It doesn't know that a solution has been arrived at in some other organism. It can't think, wow, the salmon have that elegant solution to the problem. Why don't we evolve towards that in the turtles? It's not an explanation that's possible. Now, conversely, it's not surprising at all to see an intelligent agent know of a solution to a problem and apply that same solution under different circumstances over and over and over again. This is what we see intelligence do, and it's not what we would expect from an unguided process.
6, 5, 4, 3, 2, 1. MDIS, we have ignition, we have a liftoff.
On September 5, 1977, the Voyager 1 spacecraft embarked on a mission to explore the outer regions of our solar system and interstellar space. Voyager was equipped with an array of scientific instruments and a message from Earth to the rest of the universe. A gold-plated disc imprinted with images and audio recordings that illustrated the diversity of life and culture on our planet.
As the Secretary General of the United Nations, I send greetings on behalf of the people.
These cosmic postcards included 116 pictures, greetings in 55 languages, and a medley of iconic music and sounds. Among them was a haunting refrain from the depths of the sea. The songs of the humpback whale.
I think the decision to include these songs on a mission into outer space reflected just how popular they were here on Earth. In fact, in 1971, an album was released by Capitol Records. It sold millions of copies, and the whales became rock stars, and they fascinated science and the general public ever since.
These songs are loud, long, and among the most complex vocalizations in the animal kingdom. Only male humpbacks sing like this, and always with their mouths shut tightly, so technically, they're humming. Songs can last from 3 minutes to more than half an hour, and are repeated, almost verbatim, in sessions that often continue for days. If one whale introduces a variation on a theme, it is copied by other whales in the vicinity. Songs can travel and be heard 1,000 miles from their source.
The structure of the songs can change dramatically from year to year. Humpback populations in the Pacific, Atlantic, and Caribbean each compose new arrangements that are unique to their specific locations. And typically a song has 4 to 12 different themes.
After more than 4 decades of research, exactly why the whales sing is still not clear. Scientists have long speculated that the songs are mating calls used during courtship, or possibly as a form of sonar to help identify and track the location of nearby whales. But while these enigmatic solos remain a mystery, other features of the humpback's behavior and anatomy are much better understood. The humpback whale is one of the largest animals on Earth. Adult females measure up to 50 feet and weigh 40 to 50 tons. They can live for more than a century. In warm tropical waters, a female gives birth to a single calf every 2 to 3 years. The whales breathe through twin blowholes that expel a double stream of spray visible for miles. Then they quickly inhale enough air to fill a pair of lungs, each the size of a small car. When it dives, a humpback can hold its breath for up to 45 minutes. Their underside is lined with grooves that run from navel to chin. This accordion design allows a humpback to expand its throat as it intakes huge quantities of water whenever it feeds. The whales have no teeth. Instead, they are filter feeders, straining 50 pounds of krill or small fish with every mouthful. Humpbacks have massive flippers, the largest of any animal. The whales raise them to work as solar collectors, a behavior that helps regulate their core body temperature. Their powerful tails are legendary. The flukes measure up to 15 feet across and can propel the whales to depths exceeding 700 feet.
You can say majestic, you can say breathtaking, any number of adjectives, but really in the end the language fails. You have to be there standing on the boat looking at them. They're as long as a city bus. You know, they've been down underwater feeding, up they come. How do you describe that?
This sense of sheer wonder is universal, and our fascination with the largest creatures in the Earth's history has sparked a rigorous search for the explanation of their origin. It is a search that is both an icon of Darwinian evolution and a challenge to its validity.
You look at its features, it's warm-blooded, it has mammary glands, it's clearly a mammal. Yet, its whole life is in the water, so there's a puzzle for evolution. How did this come to be?
The Darwinian narrative of whale evolution is familiar. A four-legged terrestrial mammal, the size of a wolf or sheep, undergoes a series of gradual biological changes over millions of years.
The standard textbook account I take to be artistic license. When you look at the problem of being a land mammal that finds itself, speaking loosely, in an aquatic environment, and you've got to conduct your everything there, including reproduction, you have to have the coming together of a number of adaptations. And that is unfathomably complicated.
The scale of these adaptations would have to be massive, including a remodel of the skull and muscles to move the nostrils to the top of the head, the conversion of front legs into flippers, a reconstruction of the skeleton, including a ball joint that allowed the tail to move up and down, the transformation of a few dozen teeth into hundreds of plates lined with brush-like fibers, the reorganization of kidney tissues to accommodate the intake of salt water, lungs dramatically enlarged and renovated to withstand the intense pressure of deep dives, the inclusion of a blubber layer for insulation in cold water, and modifications of ears, eyes, and skin to work effectively in an aquatic environment.
Just think of all the parameters that would have to be modified, and then multiply that by, I don't know, 1,000-fold, or more than that. That's the scale of the problem that you're dealing with.
In the context of Darwinian evolution, the most crucial adaptations would involve the male reproductive system. To optimize the whale's mobility in water, its reproductive organs would have to move from the exterior of the animal's torso to inside its abdominal cavity. But to produce sperm, the internalized testes must be cooled and kept below core body temperature.
Unless it's kept below, you'd have no sperm production, period. And in evolutionary terms, sterility means it's no-go. You don't count in the race of life, so to speak.
One of the necessary conditions of natural selection is the ability to reproduce. You can't have natural selection if you don't have reproductive capability. You can't make the sperm, you can't have reproduction, you can't get natural selection operating. So you've got to solve this engineering problem.
As a male humpback swims, it generates heat, raising its body temperature. To prevent sterility, the whale relies on a refrigeration mechanism designed into its circulatory system. In the non-insulated regions of the dorsal fin and tail, blood is cooled and then transported through a network of veins to the whale's abdomen. Here, beneath a layer of muscles, a web of veins and arteries surround the testes. They are arranged so blood flows in alternate directions, and heat from the warm arteries radiates to the cooler veins. This transfer lowers the temperature of the blood to a safe level before it is channeled to the reproductive organs.
It's a remarkable solution to that problem. It's beautiful, it's anatomically complex. It involves what is called, borrowing from the Latin, a miraculous web of arteries and veins. But can you explain it by some smooth, gradualistic, textbook scenario, little change, fixation? No, it doesn't fit the Darwinian model. In my opinion, you're looking at just a suite of characters that had to have been integrated from the get-go. I mean, it's a non-gradualistic type of change. So the cooling system makes sense because you have internalized reproductive glands. The internalized reproductive glands, however, are a no-go unless you've got the cooling system. You can't explain the emergence of one without the other.
Since 2001, biologist Richard Sternberg has used widely accepted data on mutation rates and population genetics to study the Darwinian model for whale evolution. Sternberg has focused his research on natural selection and the probability of coordinated mutations, the genetic errors in a DNA molecule required for macroevolutionary change.
I mean, I say it's a numbers game. You have to explain it in terms of a number of coincident mutations that just happened to arise and be put in the right combinations to reshape the vertebral column, to reshape the musculature, the nervous system, the eyes, the ears, and on and on and on.
So let's imagine that the transformation you wish to achieve is transforming a leg from a terrestrial mammal into the flipper of a fully aquatic mammal like a dolphin or a whale. Now, We look at our set of mutations that are required. Let's say we've got A that's going to affect the bones. But you think about your own limb, it's not just bones. There are muscles and tendons and nerves and associated behaviors. So you look down your list of mutations and you go, well, I've got A starting my transformation, but I need B, C, D, E, and F as well. So the challenge of cooperative mutations is to have these events occur in space and time in such a way that they can jointly work together, cooperate, to bring about the transformation that you need. But you know what? Those mutations, they're accidents in the genetic material. They just happen. So you're essentially relying on luck. And odds are you're going to miss the target by a mile.
In 2008, researchers at Cornell University calculated the time required to generate randomly a single pair of cooperative mutations in a population of large mammals. Richard Sternberg applied these calculations to his ongoing analysis.
And they came to the conclusion that, sure, you can get these two coordinated mutations, but it is a problem. It's a problem because you need, as far as we know, on the order of well over 100 million years to give you the coordinated mutations that would, just two, that would give you some beneficial modification. And by my reckoning, to account for the transformation that you'd see, you need far more than two mutations.
If two cooperative mutations are established in a population of mammals only once in 1 million centuries, then a significant challenge to the Darwinian model rises from the dust of the earth. According to the most generous interpretations of the fossil record, the longest possible time frame for the theorized evolution of a land-dwelling animal into a whale is 9 million years. That's a fraction of the 100 million years required to produce a single pair of cooperative mutations, and just one of the countless anatomical changes necessary for natural selection to succeed.
So when you just plug in the math, and there are various ways, I mean, what you've done is you've exceeded the time that the geological record provides you with. And then you start saying, okay, now I'm going to rely on these coordinated changes, and it's kind of game over.
You don't have to have a PhD in mathematics or population genetics to see where this is heading. Even if I grant you millions and millions of years, 5, 10, 50, 100 million years to bring about this transformation, you still face these very real limits of population size, mutation rate, generation time, and the number of features that have to be modified. If the process in question is not going to happen, it's not going to happen, and it really doesn't matter how much time you have. So have all the time you want. If this transition occurred, it did not occur by an undirected Darwinian process. That simply is not possible biologically.
Darwinism provided an explanation for the appearance of design and argued that there is no designer, or, if you will, the designer's natural selection. If that's out of the way, if that just does not explain the evidence, then the flip side of that is, well, things appear designed because they are designed. And those designs simply seem too efficient and too optimum to have been cobbled together by some haphazard mechanism.
Snorkeling with my daughters off the coast of Mexico a few years ago, we saw all these tropical fish coming by. And it's just over-the-top, gratuitous, exuberant beauty. This enormous canvas of incredible marine life. And it draws me to design. Why? What triggers the inference of design? What triggers that conclusion? What triggers it is the evidence of planning, is evidence of foresight, is evidence of a global architecture that only a mind can bring about. The data from genetics and molecular biology and a host of other fields have proven impossible to reconcile with undirected material causes. And if science is an open-ended search for the truth, regardless of where the evidence leads, then what difference should it make if it leads to an intelligent cause? I want to understand the world. I want knowledge. I want to know what's true about the world, and the assumption that living things are not random assemblages, but that there's a rational logic underlying them, that assumption is enormously fruitful for yielding knowledge. And if it's knowledge that you want, that's the direction you should go. All you need is an open heart, open eyes, and an open mind. And that signal of design that's there in nature will be clear to you. Unmistakably, it's everywhere.